go into a little bit of we saw that the biology seems to interact with all this information, and it seems to confirm a lot of the information. So we can come at it from different perspectives. And one of the perspectives I was coming at it from is the geometric perspective, obviously. And I was playing with the interaction of the spheres interacting. If you put a sphere around each tetrahedron of vector equilibrium, they will intersect. Or if you put a sphere around each tetrahedron of a star tetrahedron, they will intersect. The intersection pattern looks like this. It looks like petals or lobes. Interestingly, the lobes, vertices match the vertices of the octahedron cavity inside the metric. That is, they don't fall at weird angles or anything. They just fall directly at the vertices of the geometry. So now you have curved space interacting with linear geometric space. And I start to ask myself these questions, like, what are these lobe-type structures? Now, let's go back in time. I was still in my van. This was like 4 years later, right? Still studying, and I was reading a lot of physics about waveforms and so on, and it was really intriguing, but it was giving me a lot of headaches. And I was getting headaches because when you look at those things, waves, they typically are represented as a sine wave, right? Something in this fashion. And we are given in general that this is the wave frequency, the wave amplitude, and the wavelength. And that's basically the parameters we describe in wave dynamics. And I was getting a headache. And I couldn't figure it out. I was like not able to visualize these waves. I was trying to visualize my view of the universe and to like see how the wave dynamics kind of fall into it. How does that all interact and where it all fits in? And I didn't quite understand what a wave was, and so I was trying to read up on it, and I was getting more and more confused. And eventually I just said, okay, I gotta kind of go back to the basics. And so I drove my van up to Alpine Lake in Canada, where you have those turquoise Alpine Lake inside inside a mountains range, so it's very calm. And I grabbed a bunch of pebbles, and I was sitting on a branch on the side of the lake, throwing pebbles in the lake, going, okay, how are these waves working, And I'm looking at these rings coming off the surface and all this, and it's kind of a simple approach, but I was kind of visualizing it, and I could see that if I took the waveform on the surface of the water and I sheared them, or if I divided them, I could see that it would generate this pattern, this waveform. But I thought, well, this is kind of an artificial way of looking at it because, well, the rock is sinking. It hits the surface tension of water, and then it pushes the molecules out, and then this wave comes out. And I thought, well, you have to account that the rock has to sink in order for the wave to happen. So how do I account for that? And I was getting confused, and I couldn't understand it all together. And then I thought, but wait a minute, and I thought, if the rock is sinking and the wave is being produced, then it's like more like a vortex. And when I thought of that, it hit me. Oh, wait a minute. I'm thinking in 2 dimensions. You see how that flat two-dimensional planes gets you? You know, that Euclidean flat space? Well, in this way, you know, we think of waves as like, you know, traces on an oscilloscope or something like that. But actually, a wave is a three-dimensional vortex. I realized, oh my God, if this was in 3D, this would be a vortex along an axis of rotation. And it hit me, oh my God, waves are 3D things. We live in a 3D world. It's not a flat thing. Flatness does not exist. There's no such thing. That's a concept of man, not a fundamental structure of nature. Euclidean flat space are irrelevant to nature. And so I totally got it, and I thought, oh yeah, you know, when you think of I looked at the sun and I thought, oh my God, I don't know how many times I thought of a waveform leaving the sun and coming towards me doing this up and down thing. And it's like, you know, not anything in the universe does up and down. You know, it rotates, it spins. And so a waveform coming off the sun is a vortex that's touching me, that's hitting my eyes, that so on. And I realized that this was fundamental, that we commonly, because, and you know, if you ask a physicist, he'll tell you, oh yeah, it's a 3D vortex, but we don't think of it that way. I mean, if he's well educated, he'll know that. No. And we don't think of it this way because it's too complex. We flatten it up so that well, okay, but if you flatten it up, now you don't have angular momentum. You don't have the spin dynamics of the geometry of space, you know, that generate the vortex in the first place. So I was like, oh, okay, so I'm thinking about all this and I'm getting excited about it. And I laid back on the, I get excited, you know, you might have noticed. And so I laid back on the side of the lake and I was looking at the sun setting behind the mountain tops, which happens quite early in Canada. And then I noticed that, well, actually late in the summer, but I noticed that the sun was going behind the mountains, and a thought came to my head, isn't it cool how we always think the sun is going behind, but actually it's the earth that's rotating? And when I thought that, something hit me. Another thing hit me. I realized, well, these waveforms, dynamics, have to do as well with motion in space. Things move not in this up and down motion. And then I thought, wait a minute. And I thought of the solar system, and it hit me. Typically, and if you have children, please, if they go to school, they're all going to get told that the solar system looks something like this. Let me try to erase this.